Hello and welcome to the ninth episode of the RockyTerrain podcast. Today is March 8th, 2021. My name is Thomas, and with me, as always, is Dennis.
Hello there.
Yeah, so in today's episode, we're gonna talk about the NASAs Perseverance mission and about the geological context of this mission. So interest in the science objectives and the geology, then you, are welcome to stay. Otherwise, before we will go into our main part, we want to talk, as always, do this little introduction part. We're going to talk about our news and our study in university or at our work. And for that, we will start with Dennis. So, do you want to talk about something?
A couple of things. Maybe at first I would like to address that we've been a bit late with this episode. And that's because we're both pretty busy right now. Thomas had a lot of work to do with conferences. I am currently preparing for some exams, basically the final exams from my bachelor's degree. So yeah, we have always said, and we will keep it that way, that our studies have priority for us, of course, and that's why we've been a bit late. Yeah, so much for that first explanation. I have once again switched rooms. So I have the feeling that I keep doing this. I have the feeling that this is a never-ending story, because at first I was recording in our bedroom on my desk with my laptop. Then I had to, at times, leave the bedroom because my girlfriend had to go to work pretty early in the day. Then I had this whole story that the delivery of my PC was delayed and delayed and delayed for weeks and weeks and weeks. So we even refitted our schedule to meet the delivery, which then didn't turn out well because it was delivered on time. And then I finally set everything up in the bedroom. And now, once again, because, it's pretty impractical, because I tend to work in the evening often. You and me, we record in the evening and stuff like that. And when she has to go to bed early, that's pretty impractical. So we've decided to switch desks, so hers is now in the bedroom, mine is now in the living room, and I hope that at least until we move to Bonn later this year, this is going to be my final setup. So
update to that story next week.
Right. Hopefully not, but here we are. Other news, the most major news from my side. I have finally started working on dinosaur bones, which is very, very exciting to me. Yeah, clap, applaud me. Honestly, this is pretty cool because, I've talked about the fact that I'm working at our Natural History Museum here in Münster, and I'm working in the collection of said museum. And I was occupied with sorting mammal bones, Ice Age mammal bones of the past few months. And right now we're pretty much through with the part we want to get through with. And now the next task is to sort dinosaur bones. These are lower Cretaceous dinosaurs from a dig site in the Sauerland, German, English. Here in Germany, in northwestern Germany, these are, at least for the overwhelming part, Iguanodon bones. So big herbivorous dinosaur, one of the first dinosaurs to ever be discovered, this genus, Iguanodon. Basically these bones are pyritized, so during fossilization, a mineral called pyrite or fool's gold, as some people might know it, has become part of these bones, and yeah, this results in these bones being pretty unstable in contact with the atmosphere. They tend to fall apart in contact with the atmosphere. So these bones have to be stored in airtight bags, and our task right now is to go through all these dinosaur bones and to have a look whether these bags are still sealed up, still airtight, to note if they're not, and basically to fit some numbers. So pretty cool, because you never learn more about something than when you're actually working with it. And right now I'm actually working with and looking at dinosaur bones, which is pretty cool. Feels it feels as if my lifetime so far would have been focused on this singular moment. This feels like the fulfilling of a dream. I mean, working on dinosaur bones. This is.
I get it, but it sounds a bit funny because, I mean, you look at bags to see if they're still closed.
No. It's because of the bones, but yeah, plastic bags, I don't know. Interesting as well.
I understand.
Yeah, but that actually plays into the final part of my news section, because I will announce it right now that next week we are going to talk about, among other things, this very dig site, because we do still work at a dig site, a lower Cretaceous dig site in the Sauerland each year. We are active there for about 4 months every year. This is actually my 3rd season this year working there. And, well, details in the next episode, but these two dig sites seem to have some certain connections. The fossils are pretty similar, the age is very similar, the sediment is pretty similar, and yeah, this inspired me to finally talk about this episode, because right now, just to work with these bones, of course, I'm going through the literature, through the description of the fossils anyway, so why not compile all of this into the episode?
Yeah, so next week is for me an listening and asking question episode.
Yeah,
pretty similar to the one last time for you.
Yeah, or this week.
Yeah.
For the most part.
Yeah. Oh, let's see.
Thomas, what about you?
Yeah, so for me, there were also some reasons. I mean, you've already said that because you already talked about it. That's what I wanted to say. So I'm currently having a conference next week, the Lunar and Planetary Science Conference, for which at the beginning of the year I've written 2 abstracts. So I basically entered the conference with 2 different topics. And one is a topic about my bachelor thesis. And I have one talk at this conference with this topic. And this year, because of course it's online, normally this would take place in Houston, Texas. But since it's online, everything is a bit different. And for the conferences, they are not live. They have to be pre-recorded and then uploaded so that everybody can watch it, the video, over the, I think, time of the whole conference. Like, I guess. I think after the conference, it's then taken off again, but I'm not sure about that.
But it's not going to be available anywhere, is it?
No, I think only if you have registered to the conference.
Yeah, unfortunate.
Yeah, I mean, you know my talk.
I know it. Yeah, I've seen it, but yeah. Unfortunately, it will remain among the eyes of a few selected of your friends.
Yeah. And then there will be also a small live section, like a Q&A section, where people can ask questions next week on Friday, which is also my birthday. That's gonna be interesting. Yeah, so I've made a pre-recording talk, and normally I would have thought that would be quite easy to do, because I love giving presentations. I love giving talks. I love just telling people what I've learned currently or something like that. I have a lot of fun with that. I'm not that nervous while doing this, and normally people also like it when I'm giving talks or presentations at the university, for example. So I was really looking forward to that. However, turns out while pre-recording or while giving live presentation, it's very easy for me, or not that difficult for me. Doing pre-recording talks seems to be quite a difference. So some aspects. First of all, I've started entangling myself in my words every sentence. I had to restart basically on every slide. I had to do a lot of cuts. Also, it was quite difficult for me to get it on time. Like it's not allowed to be over 15 minutes. Normally in a live presentation, you would go like, I don't know, 20 seconds above or 30 seconds above, and some guy will just tell you, and okay, it's okay, or everything's all right. But in that case, if it's longer than 50 minutes, you just can't upload it. And yeah, it was quite difficult to do. But still, it worked in the end.
Yeah.
It was a lot of work.
You should have listened to the audios I got from him over WhatsApp. It was pretty much done. He was spent.
Yeah.
Yeah, but honestly, I can truly imagine, because we don't really have too much experience having talks.
Yeah.
How could we? We've only just started really getting into academia. You have more experience than I do. A bit more at least. But yeah, I can imagine, because while having a talk, you don't really think about mistakes you've made, because nobody is going to remember it anyway, as long as your presentation is good. And now it's in a video form where, in theory, everybody can go back to it and to it and watch it over and over again. But once again, I think you and me, we're both two guys who tend to think about such things too much.
Yeah.
So because honestly, our talk was pretty good in the end. I really liked it.
Yeah, in the end, I'm also now kinda. It's okay now. Let's put it that way. I'm happy with that I'm finished, and I think it looks good, and the information is correct that I say, and I think that's the most important part.
Yeah.
And good example for like doing small mistakes that would normally not be such a large problem is that, for example, I said northeast trending instead of north-south trending. Now, if that would happen in a live talk, everybody recognizes that you're showing a north-south trend, and that's it. Everybody knows, okay, you've misspoken. Maybe someone is asking you then in the Q&A section, and it's okay. Nobody matters.
Nobody matters.
No. I wanted to say it doesn't matter. It doesn't matter. But when you're doing a video, basically, then you want everything to be correct, and then it's different. So yeah, so much for the talk. And then I've had a poster to do for my other project that I'm currently doing with the DLR in Berlin. We're working on ExoMars, so on the Mars rover from the European Space Agency and the Roscosmos, so the Russian Space Agency, which is also focused on the search for life, similar to Perseverance, and I'm probably also going to talk about it later in this episode. And for that, we did a poster. Now, this year, there's like an online tool where you can create posters. At first, I didn't like it, but in the end, I kind of liked it because it was very easy to do. It was very convenient to do a poster, but they're like only very. You don't have the ability to change anything really. You can just choose a template, so the number of boxes, but you can't change, for example, the size of these text boxes. And all you can do basically is change the colors or the background, and that's it. So, I mean, you can add videos, for example, or audio, which I haven't used, but you could. But otherwise, there's not much you can do about it. But still, I think that it actually looks really good, what I've done. And I tried to get at least close to an eye catcher as possible. And at least I like how it looks like. And yeah, in the end, I kind of enjoyed it because it was very convenient. And maybe for future conferences, if there are, or if there will be another online conferences, I hope that they will just add at least some small functions.
Yeah, I mean, I would say hopes are that things won't have to be online next year, but as of now, I just tend to stay a bit more pessimistic.
Yeah.
But
also I think that maybe like even if everything is, finished basically with Corona and COVID and everything is as normal as it can be, maybe smaller conferences will stay online just because people realize maybe it's not worth it to pay like a lot of money to prepare everything, or just to pay the planes and everything like that. So I think maybe like smaller conferences will maybe stay at this online format. I don't know, but I could imagine it at least.
I mean, it depends really, I think.
Yeah.
Because
it depends on the conference.
Yeah, definitely. For example, my hope was that the Flugsaurier... German word of the day. That the so-called Flugsaurier, pterosaur, pterodactyl, flying reptiles of the Mesozoic, brethren to the dinosaurs, legendary, great animals, look them up. I'm really into pterosaurs, and so I do keep following updates on that on this meeting, just because I have the dream to one day be a part of that in some way, shape, or form. And for example, I think this one is very well still planned to go ahead in person next year, because I don't know. So, I mean, it's a rather small conference. I think what was it, about 60 people, 50 to 60 people meet there.
Oh.
Yeah, I mean, it's a small field. Paleontology in general is a rather small field compared to other ones. And pterosaurs is even smaller than the dinosaur community. I mean, it's changing currently, I would say. But, yeah. I don't know. This one is going to go ahead. I don't know. I think it really depends on the exact field and how familiar everyone is. Because I think in cases where people do already know each other pretty well for the most part, maybe you'd like to see them.
Yeah, I think for these conferences it'll probably be in person, which I think is good. But yeah.
Anyway,
yeah. Mars. That's also the topic of today's podcast, and we're gonna talk about Mars and Mars rovers and maybe life on Mars after the small break in our main part. So see you there. It's now directly 426 hours since Perseverance landed on Mars. The landing did take place on the 18th February 2021. And Dennis and I actually watched it together over Discord.
Yeah, indeed. Right. Directly after our last recording.
Yeah. How did you feel while watching it?
Actually, every time I watch something like that, I feel a bit sad that I didn't go into planetary sciences, because I don't know. To me, this really encompasses everything you think about when thinking about science, This team which has worked over years and years on this. which has invested so much time and effort, and it all comes to fruition, hopefully. And then everybody is waiting, and yeah, everybody is anticipating the landing. It's I don't know, this tension and the relief afterwards. I don't know. I always think it's great. It's a feeling not comparable to anything else in the world of science. And yeah, damn it, I'll never get to feel that. But pretty cool. It's always something special.
Yeah, I was really nervous. I mean, I know I was really nervous at first, but I actually had the feeling the closer it get to the landing, for some reason I was less nervous. I don't know. And then while watching the beautiful NASA stream, as always, with their beautiful animations.
Yeah, that was a bit weird. That was a bit weird because the footage wasn't really prepared. It was a simulation, and someone just basically fumbled around in the animation, twisting the model of the lander during the animation. I mean, you could follow at which stage you are, at which stage of the landing they are right now. But it was just this weird animation with someone fumbling around in it and twisting the model a bit. Yeah. I found it weird that they didn't have anything prepared.
I mean, I don't know if that's like a live updated, I mean, live in quotes, but, like an updated version of the landing. So when the rover, for some reasons that are very bad, but for some reason speeds up, if like then the footage would have also sped up. I don't know. But,
I don't know. Yeah. Weird. But what I actually found more interesting was the control room, because as we've said, these people are under so much pressure, and I always love this moment when you see the relief on their faces and this genuine demonstration of joy, just joy, and this huge burden falling off from their shoulders. And by the way, one guy had this, this cartoon dog from the "This Is Fine" meme. The dog sitting in the burning house on his table, which was pretty interesting. This is fine.
Yeah. I can just imagine how that feels like.
I think
just years of work.
I think I would really get along with this guy. Good sense of humor.
Yeah, I also really enjoyed it. Of course, after that, I was on a small walk due to this through the city, just thinking again about it. Yeah, so did you see the video of the landing? I mean, of course you did, but...
Yeah. Afterwards. I wasn't expecting that. Did anybody know that they would release it?
No, I mean, I did not know if you saw that, but they had like this trailer for this conference. And this trailer was like complete hype. Like it was something... It seems like a trailer for a movie. And it was just such a contrast to like the live show that we've seen before, as we said. And now we had like this high quality trailer for this conference and at the evening.
Yeah.
For this press conference. But since I know, or like, I have just thought that it would be like a sequence of images, like a movie in quotes, like a sequence of every, 10, 15 seconds, one image or something like that. Which would have still been amazing. I mean, I would have been probably blown away by that too. But I have not expected such high quality landing video. That was amazing. I was really blown away. Completely blown away.
Definitely. It's so great. We keep repeating that, but what a time to be alive. I mean, just imagine what really high quality images we've gotten over the past few years, be that
Yeah.
from the Juno mission to Jupiter. And oh my god, Jupiter is the most beautiful thing I've ever seen.
Also Saturn.
Saturn, yeah, now this landing video. It's such a great time to be alive, really.
I mean, when now seeing like the landing method, I will say, in video, it makes it so much more. How do I say that? So Perseverance and also Curiosity landed with the sky crane maneuver, which is called. So basically, at first the descent, the landing model basically uses what are they called?
Parachutes.
Parachutes, right? So they use parachutes for like the upper meters of Mars to slow down. And then, but since the atmosphere is so thin, they then have to use rocket engines to land the rover. But since these rocket engines would then blow up dust and rocks and all the material, the rover could get damaged. So what they're doing is they're using like a jetpack, and then they lower the rover itself by a sky crane, so by cables basically. They let the rover down by cables till it touches the ground, and then the sky crane will detach and fly away.
It just shoots off, right?
Yeah, it just shoots off and then
Without
crashes somewhere.
Yeah, it's not meant to be recovered or reusable or anything.
No. It just has to crash large, far away from the rover. And I don't know. This is just. I mean, it makes sense to do it like that, but still, there's so many aspects that can go wrong. This whole operation seems like just on large flex. Yeah. Like imagine they're trying to figure out a way to land these large rovers, and then one guy is like, "Yeah, we could use like a jetpack and then let the rover down by cables." And everyone is like, "Oh, what's wrong with you? We can't do that." And then over time, they're like, "Oh, maybe that is the way to do it."
And it's amazing that we can do these things at all.
Yeah, it's so amazing. So about Perseverance, maybe to get into the podcast.
Indeed.
Perseverance launched on July 2020, so last year. It was to get a bit of history very quickly. Curiosity, or the idea of a new Mars rover by NASA was announced in 2012, so after the landing of the Curiosity rover. The idea of having new Mars mission was already an idea since 2010, basically. And then they had the idea to do a mission return, a sample return mission, and we will talk about it later, then in 2011. And then in 2012, they said, well, let's do this all in one and do a Mars rover and then combine that with a sample return mission. And that was 2012. So since then, they are working on that mission. And here we are. This actually, it's quite a fast mission, don't you think? For such a large rover?
Absolutely.
And it has a reason. There's a reason why it was that fast, but I think we will talk about it later when we talk about the rover itself.
Yeah. It's actually, I was also quite surprised how quick all this went, because I was expecting early 2000s maybe. Because, things have to go through a lot of different instances, through a lot of different offices. And
especially with NASA.
Yeah, and surprising, really surprising, but the more brilliant that it worked out like that.
Yeah. Actually, maybe it's the best way to talk about it now. So the reason why it was so fast is that it's basically an updated, in quotes, version of the Curiosity rover. Yeah. It actually uses some spare parts of the Curiosity rover.
I didn't know that.
It's But it's an updated version. It's heavier, about 200 kilograms heavier. It weighs around 1 ton, 1 metric ton, and Curiosity weighs around 800 kilograms. So there are some things that were added.
They're both cars. We'll link to that in the YouTube description. So also, if you're listening on Spotify or Google Podcasts, when you will look either at the NASA website for Perseverance, or whether you will look at the links in the description of the YouTube version of this podcast, there are actually also 3D models of this rover. Yeah. If you're curious or you want to follow the instruments we're going to talk about, and this also goes for the landing zone. So yeah, check that out. And I think it's also pretty interesting to see these rovers for yourself, especially to get a feeling for the scale, because oftentimes I always tend to think that they're smaller, because I tend to forget that these are car size.
Yeah, but then there was Opportunity and Spirit, and I thought these were also as large. But they're actually incredibly small. After I saw an image of them with people standing next to them, I was quite surprised how small they are. But Perseverance, and Curiosity are car size. Yeah. And really heavy.
Impressive. Very impressive.
Yeah, definitely. So yeah, because it's it's an upgraded version of the Mars Science Laboratory or Curiosity, they were able to build it really fast. And this is called their heritage approach. So basically, I saw somewhere describing it like evolution, like biological evolution, trying to use something that already exists and try to build it so that it fits your new requirements. And it's also much lower cost overall, of course. So the Mars Perseverance Rover is focused to search for signs of ancient life on Mars. That's the main focus. It tries to figure out astrobiological questions, but also, of course, geological questions. So the main objective is whether Mars was ever inhabited, yes or no. And what this whole mission is built around. It also, of course, tries to provide new insights for the Mars geology, planetary science, and also for future human missions to Mars. It's also, at some parts, and I'm going to talk about it later, technical demonstration mission. Now, I think we can go through the main objectives of the mission. So while researching, I actually wanted to have because I did know that from the ExoMars rover, a step-step plan what they're trying to do. When they're trying to do what. However, wherever I search, it does not seem like this plan is at least public. And they more have this overall ideas that they want to do. And it seems like they more or less then trying to figure out once they've landed how to approach. There are, of course, some timing constraints and everything like that, but it seems like more that they want to go on more open approach. Which, of course, makes sense since the lifetime, or the minimum lifetime, is about 1 Mars year, which are 2 Earth years. So that's a really large mission. And then, of course, it makes sense to be a bit more open for possible timing of different activities of the rover itself.
Yeah, and they're also going to explore this crater in detail.
Yeah.
We are going to talk about the crater later on, after the mission profile and the instruments and the technical aspects. But they are going to go into detail with this crater because it's a very complex structure. A lot has happened there in some way, shape, or form, and therefore I think it's pretty advantageous to be open for spontaneous plans and spontaneous ideas.
Yeah, definitely. Also about the landing site itself, Dennis will tell us later a bit more, and I'm trying to focus on like the rover side itself. Okay, so let's go to the mission objectives. And there are like different level of requirements that they want to achieve. And the first one is just an overall idea. They want to characterize the processes that formed and modified the geological record. And search for evidence for an astrobiological relevant ancient environment and geologic diversity. And that's why they've chosen the Jezero Crater, and this is the one we are talking about later. So the overall mission is just very broad. Yeah, by the way, we want to figure out the geological record and also the astrobiological, about the idea of the astrobiological relevant environment, something like that. So very broad. While reading that, I figured something out. Most of the, it seems like always geology is the science that sometimes is kind of overstepped. You know what I mean? Like you have astrophysics and anything like that, and geology somewhere like often, that also exists, and they talk about rocks, right?
It has this reputation to be this. It's not the shiniest of topics, not the shiniest of disciplines. The results are often what is then presented, but the science itself often is not so much described in detail.
Yeah, and the interesting point is that these Mars rovers are so well known, they're basically pop stars. And they are basically geologists.
Indeed. And Perseverance is a paleontologist, to be exact.
Yeah, also. He's like a multi-talent,
a geoscientist.
Yeah, exactly. Yeah, okay, so that's like the overall broad objective. And then the next level would be they want to perform they want to study the astrobiological relevant, or they want to do astrobiological relevant investigations. So they first want to determine the habitability of this environment, of the Jezero Crater.
The former.
Could have been...
The former.
Yeah, exactly right. The former habitability, exactly. So could this place have been, in the ancient times of Mars, be habitable, yes or no? And then they want to search for materials that are biosignatures, or materials that have an preservation potential for biosignatures. And then they want to directly search evidence, if there is evidence, for potential evidence of past life. That was 2 times evidence, but I think you know what I mean. And here I think we have to explain what biosignatures are. So, a biosignature is basically just an object or a substance or a pattern, like visual or chemical pattern, that forms, or this origin is by a biological process. And then the usefulness of a biosignature is then determined if it's like, if this biosignature can only form by life, or if there are also some non-biological process that could also produce it. Like, for example, limestones, right? They can be built up by life, but also by non-biological activity. So you kind of have to be careful what a biosignature actually is, and if it has a biological origin or not. So there are further studies then needed. But yeah, that's basically a biosignature. For the Mars 2020 mission, the science definition team identified 6 classes of biosignatures for this mission. The first one is pretty straightforward: organic molecules. So if you have an organic molecule, then, well, that's of course a biosignature. Then you have macrostructures and textures, so basically fossils. Something they thought about was stromatolites, which we have on Earth, or reefs. So structures that can be seen by your visual eye, basically. Just looking at it and you see a structure that seemed or could have formed by life. We also have microstructures. So these are microfossils, just on a very small scale, like biofilms. And we have just a chemistry biosignatures. These are just chemical features that could suggest biological processing, like the abundance of a specific element that could be enriched by life. Then we have the isotopic record, and we've talked now a lot about isotopes in the last episodes. So I think we're gonna step over the explanation of what isotopes are. But also we know from Earth that isotopic patterns often can be influenced by life, for example, by carbon, where we have that life tends to use another carbon isotope. So if we see then a high abundance of this carbon isotope, it can give us the idea that life was involved. And the last biosignature would be just minerals. An explanation would be, for example, limestones, but also phyllosilicates, clay minerals, that are very interesting, and I think I'm gonna also talk about later. Is there anything else you want to add to the biosignature part?
No, because that's pretty much everything I encountered as well.
So I actually know because now I can talk about my project. So with the DLR, I'm working on the ExoMars rover, or not directly on the rover, but on a topic that is related to the rover. So the ExoMars ESA rover, the Rosalind Franklin rover, is also landing in quite a similar environment as Perseverance. And the idea that we have is we want to study a site that is like some 100 kilometers away from the landing site to see if the landing site itself is like a reference for all of the setting or if it's like very specific. You know what I mean?
Mm-hmm. Yep.
Yeah. Just to see like what can we do then with the data the rover will study. Like, can we use that for a larger global or regional work, or do we can't use it because it's so specific in this region that it does not say anything else about other regions on Mars? That's the idea.
Exactly. Basically, is it representative for the bigger picture? Is it representative of a bigger region, the planet in general, or is it pretty much its own thing?
Yeah. And this mission is also focused on the search for life. And I know that they have like this rating system of biosignatures to calculate the potential of life. Like they're starting like, if there is visible evidence for staying or moving water, like ripples or I don't know, in delta. So that would give you like ground points. Like they would give you, okay, we have this evidence. Then that would be like, I don't know, I think it was between 5 and 15 points, something like that. And then they're like, okay, are there any visual biosignatures? And then they're listed some biosignatures. And then for each biosignature they find, you will get like this rating, like points that are added to your overall rating. So that in the end, you can look at something, add your points, and then you can see like how likely this is made by life, yes or no.
Yeah.
And to show how that works, they used it for early fossils on Earth. Like also they discussed stuff where we are still not sure about if that's a fossil, yes or no. Then they used like this rating system then on Earth to see how likely it is for this very early fossils to actually be evidence of early life. I don't know how if they're doing something like that for the NASA Perseverance mission. I've found nothing. But I could imagine that they're using something similar because they have to be very careful with biosignatures. As I said, they can be also created by, or many of them, by non-biological processes.
Yeah, I mean, a good example for this discussion is what is going on with Venus right now.
Yeah.
Where you have phosphine, which the authors of the corresponding paper said was a very, very good candidate of an indicator for life because they went through a lot of different scenarios which could be potential contenders, but in the end they ruled out a lot of that. But on the other hand, you have other voices saying it could still come from other different processes and this and that. And yeah, it's a complex topic.
So these are the biosignatures, and these are important because they can give us an idea if life has existed or not. One of these biosignatures would be, for example, limestones, carbonaceous minerals that are also present on Mars, where, well, these structures, of course, shows us that there is water, or that there was water at some point in the history of Mars, because otherwise these carbonaceous minerals wouldn't have formed. But again, this is the question: did they form because of life, or did they form by some process that is unrelated to biology? And then we have another biosignature, for example, also on the mineral side. These are hydrous phyllosilicates, or clay minerals. And this is interesting because this is something that I'm working on with this ExoMars project. Now, phyllosilicates are also called sheet silicates, and that's because they form parallel sheets of the silicate tetrahedras. So on a very small scale, they form these parallel sheets, like mica or biotite.
Mineralogy,
yay. And some of them contain water. So water is built in the structure, or some OH groups. And some of them are called the clay minerals. And that's too much to mineralogy. Now we can try to interpret what these minerals are.
Yeah.
No more structures.
No, we've had enough of that, and right now I have to learn stuff like that. So my exam is going to be about that. It's basically about microscopy of minerals.
Yeah.
But this is pretty interesting, and I think you'll get to that right now, what that could mean.
Yeah, definitely. So first of all, because they inhibit water, or inhibit is the right word, because they have an abundance of water within a structure, we know that they form, or there has to be water presence to form for them. And then it's difficult to say what kind of water. So the Martian topography is quite interesting because the northern Mars is much lower in topography. This is called the Martian lowlands, and it's also a very smooth area. And the southern part of Mars is topographic much higher, and it's a rough surface. And that's why some scientists think that there could have been an ocean in the northern area of Mars. And these phyllosilicates, these clay minerals, we actually find at the possible shore region of this possible ocean. So one idea is that this large, this large area of standing water, this ocean, could have provided the water for these minerals to form. However, these could, for example, also form due to groundwater or hydrothermal activity. The water does not have to be, in form of a large ocean. There are also some other ways this water could have formed. However, just the abundance of water, of course, is important when we ask the question if this area was for some time habitable. That's the first point. Then we know that these phyllosilicates need moderate pH conditions and also a redox-reducing environment. And also, these points or these conditions favor life. So that's the next part why these minerals are interesting. Then there are many ideas actually for the origin of life on Earth that use phyllosilicates to explain the formation of life, because these phyllosilicates themselves could have served as reaction centers for organic molecules. So maybe phyllosilicates actually played an important role in the origin of life here on Earth. So that's another important part why phyllosilicates are interesting when you want to look for evidence of ancient life. But the very important part here is that these clay minerals can bind organic molecules to their structure and therefore prevent their decay. And that is interesting, or that is important, because when we talk about water on Mars, like this large ocean or rivers or lakes, anything like that, we talk about an age that was very, very long ago. We talk about the first billion years of the Martian history. So 4.5, 4, 3.5 billion years ago. That's extremely, extremely long ago. And over such long period of time, of course, these things decay. So if you have organic molecules, they would decay over that long period of time. We know that from Earth, if we study rocks that are some billions of years old, most of the biological, it's basically useless for biosignatures or chemical biosignatures, because most of them have already decayed. Now we know that Mars has a slower rate of erosion and stuff like that, so that would influence the decay rate. But the important part is that these phyllosilicates can bind the molecules and prevent them from decaying. And that's why if you want to search for organic molecules, then these phyllosilicates, these clay minerals, are really, really interesting. And that's why many of these studies focus on these minerals. For example, also Curiosity rover. Also, these phyllosilicate deposits were a prime target for the rover itself. The next big part of the mission is the sample return part. And the main goal is, well, very easy. We want to have our first samples directly from Mars. All the samples that we currently have from Mars are meteorites that were once part of the Martian surface and then were catapulted into space by an impact and then brought to Earth. So what we want to have are the first samples, direct samples to study. And the idea is following. The rover will now select some scientific interesting areas. It will then obtain samples. It will study the surrounding material, the surrounding geological diversity. It will then study the sample itself and will put them in samples, seal them into sample capsules. That will then be stored first in the rover and then basically just laid on the surface where they will then rest for the next years.
Until someone happens to pick them up.
Yeah, that's the idea. So the idea is that in some years, in the next 10 years basically, a joint ESA-NASA mission will, 2 missions basically, one will bring a lander to Mars with a small rover. And that rover will then follow the tracks of Perseverance and take all the samples with him. And then it will drive back to the lander, which will then launch a rocket again into an orbit. And then an ESA mission will come, pick that up, and bring it back to Earth. That's the idea. Maybe to explain, the samples are taken by a drill, so not just surface sample, but drilled down some centimeters, and then the samples were taken from the subsurface area. I think we will discuss that later. It's a very interesting part, but I'm a bit afraid of that part, and that's something I really want to talk about.
Okay,
later.
Now my interest is piqued.
Yeah.
You didn't tell me before.
Yeah. I think you will get me when I talk about it later. Okay, and the last part of the mission is to contribute for the preparation for human exploration. So they want to fill strategic knowledge gaps. So these strategic knowledge gaps, or SKGs, are gaps in our knowledge or information that are required to reduce the risk and improve the effectiveness of human space exploration missions. So everything that involves future human activity, basically. And they want to provide, to fill in these gaps. These are, for example, the resource utilization of propellant and consumable oxygen. This is the characterization of the atmospheric dust to understand its effects on the surface systems and the human health. To study the surface weather. And also to study some other technological things, like, for example, the heat shield that they've used. Can such heat shields then, for example, also be used for future human missions? And this, well, in the end, is the complete mission plan. So what I want to do is, first of all, geology, astrobiology, sample return, future human missions. These 4 points are the major objectives for the mission itself. Now, to provide to these mission profiles, they will have 2 Earthies, as previously said, and they have a large amount of instruments that they're gonna use. I won't present them now, and I try to stay like just the important part, like the why it's interesting, for what questions this instrument is interesting, and I not want to go into detail of the technical side. Let's start with the head and the neck of the rover.
I like that they're always presented like actual feeling, sensing beings, human beings.
There's also like the style of the selfies that they always do.
Yeah. Welcome to my forever home.
Yeah, so on top of the rover, on this head, we have let's start with the eyes, the Mastcam C. This is a pair of multispectral cameras so they can do color images. And, well, they are the eyes of the rover. Maybe not direct the eyes of the rover, because the rover itself has like 6 cameras that are distributed through all of the rover to see possible dangers and anything like that. But these are like the 2 main cameras that we want, or from which we get the beautiful images that we already can see and will see in the future. Yeah, so this camera is, it can do panoramic shots, it can do 360-degree shots, it can zoom basically to get telephoto images of individual targets. And, well, of course, it's also a thing for the public. We want to have good images to, advertise the mission. But it also has a very important geological or scientific approach or context, because geologists, we work a lot with our eyes. We go somewhere and then just look at the outcrop, look at the rocks, see patterns, try to see patterns from the distance, try to see patterns close up. We need our eyes. We can then use data and numbers to give us more ideas to conclude some things, but we need the context. And that's why cameras are actually important. We want to have the large context, see the large area, but then the camera has also this telezoom, where then we can look at individual rocks, for example, or the surrounding material of a rock to get then a closer, smaller context. Yeah, and that's a camera they get the beautiful images from. So if you don't know, you can go to the NASA website, and there's already a raw image website where you can see all the raw images that are made by the rover itself. There are already over 8,000 images uploaded. I've gone through some, so like every day in the morning I go through some of the images. There are already some very interesting ones.
What about storage space? Just a quick question, because often they're limited. They have a limited amount of data they can send back, or image data. And you are the one who looked into the technical side of things, so this is a huge amount of data. And is it limited in some way? Did you read that?
So I searched for the storage space, but the number I found was incredible low. I haven't noted it, but it wasn't that large. It was some gigabytes maybe. It was extremely low. But I think what I do is following. The mission has a very high energy antenna, and I basically just send everything.
So there's no background memory, or I mean, I am not really the one who knows much about these things. I'm always more the type of guy who was interested in engines and gearboxes, less in computers. So basically, it just sends it out, and that's it.
As far as I know, it does not have like a large storage. At least not in the mission profile papers. And I did not find one that was specifically to the memory of the rover. Maybe. I have to look that up for the next time, maybe. But I'm not sure currently. Let's put it like that way. While we're talking about the memory, we can now talk about the brain of the rover. Do you know that they use a processor that is based on a processor that was introduced in 1997?
No, absolutely not. Why is that?
So that's an old IBM processor that was used by Apple back then, like in its MacBooks, in its very early MacBooks. The reason for that, the processor is really slow. It does not compare to like the processor that you have in your computer today. However, it works, and that's the important part. It's extremely robust, and it works.
And it's certainly cheaper than more modern components. Yeah,
but it's not about the price, of course. I mean, at that point, these are probably so rare that they are pretty expensive.
Yeah, but the part is interesting.
I mean, this processor has to work for the next years to come. Mm-hmm. You know, it just have to work. And with that, they know that it does work.
Yeah.
Of course, they also modified it so it has like a radiation shield. Because it has to, and that's the next part, it has to work in extreme environments. And like your modern processors that you have in a computer are not made for that. Mm. That's why they're using this very old.
This is stuff you just don't tend to think about.
Yeah. I mean, I thought they wanted to have like this. I mean, I don't know, how much processing data or ability they need to have, Mm-hmm. Maybe it's not that much. But it has to be not that much if they're using such an old device. But yeah. That's the brain. And then this, when we look at the head, we see this one very large camera, basically. And this is the SuperCam. And it's built upon the Curiosity rover's ChemCam. So CHEM, cam. And it's a remote sensing instrument to get ideas or to get measurements of the chemical composition of rocks, basically. It's a remote sensing Raman spectroscopy. Jeez, I always have problems with the words. It uses Raman spectroscopy. Now, what this means is that they can use it from distance of 2 meters, but still can get resolutions of up to a sub-millimeter scale at a single point. It's like an extreme sniper, basically. They see a rock in distance and can then look at the sub-millimeter scale point at that rock to get first ideas of the chemistry. That's pretty interesting. This is a very important instrument because you can look at a rock to see if it's interesting to study in closer detail or not. We can get just ideas. I mean, this is pretty accurate, but still we can get ideas of material that just lies around us, and then we can decide if we want to give it a closer look or not. So, yeah, pretty important instrument. It can observe like different styles of minerals, like for example, if you have silicates or carbonates or sulfates, stuff like that. And it can also already observe organic molecules. So this is maybe one of the most important instruments on board the rover. And then last instrument on this head and neck of the rover is the MEDA. And this just a suite of sensors that they use to provide weather measurements and dust characterization. So it measures the wind speed, the wind direction, atmospheric pressure, temperature, humidity, stuff like that. And it also can get ideas of the optical properties of the dust. And it also has microphones installed. So we have now our first real recordings of the Martian wind. And yeah, this was done with this instrument, basically. Do you want to listen?
I was about to ask that. Let's see whether it works.
Yeah, let's see if it works. So I hope you heard it. It was, you can boost it up then in the recording. But it's it's pretty quiet. I mean, I found it pretty cool, but it's, I expected a bit more, you know what I mean?
Yeah, same with me. It's the first time you played it, I didn't even notice it because I thought you were fumbling around with your microphone. It's more about the meaning. It's more about the meaning of the sound. This is the first, you said the first actual true recording of Mars wind. And so it's more about that, and it's less about the impressiveness of the audio itself.
Like what we've done before is recording, movement of the rover itself that is due to the wind. Like vibrations of the rover, and then try to, use these vibrations to then put again into sound waves. But this is like the first time that we use an actual microphone. They also actually should have recorded the landing itself, but that didn't work. I don't know why. They have not gone into detail yet. But that did not work. So I don't know if both of them are correctly working now. But at least we have our first recordings of Martian wind. So now we can maybe get an idea of how it is to stand there. Listen to the sound of Mars and slowly suffocating.
All right then.
If you can hear the sound of the wind, then you probably don't have your spacesuit on, right?
Yeah, you should be in trouble.
But that's the instrument, basically the ears of the rover. And then to maybe go a bit quicker through the other instruments, we have this robotic arm located in front of the rover, and this has also two very important instruments on board. So first of all, it has a drill to drill into the subsurface, and then two analytical instruments. So first of all, we have Pixel. Pixel is an X-ray fluorescence spectrometer. And with that, we can do Well, first of all, we can of course do chemical analysis of the rocks in the soils, but we can do like small maps of this area. We can do images and microstructures in a micrometer scale, and then we can do maps of the element distribution in these very small regions. So we can, for example, look at a microstructure that may be a fossil, and then we can do a chemical analysis of this whole region and see if there are like variations of element abundances and stuff like that, to then see if there are like correlations between the structure and the abundance of specific elements. That is then very interesting if we have a lamination of some sort, or if you want to study like if there are individual grains that are different in the chemical composition. And yeah, to get like that, also an emission profile for that instrument. So first of all, they want, of course, just a spatial correlation of elements to constrain the mineralogy. Then they want to use element maps to recognize textures or microstructures that are not apparent in visible images. Then they want to like look at individual sedimentary grains. They want to look at laminae or like intrusions, very small intrusions. And then they want to see if like these element abundances have recognizable characteristics, like, for example, if they are due to alteration or something like that. And just to get an idea of the overall bulk rock chemistry, basically. So that is also very useful. I mean, I don't have to say that because all these instruments are useful, otherwise they would not be on board. Yeah. Then the other instrument on the arm is Sherlock, of course, named after Sherlock Holmes. It provides high spatial resolution of the chemical composition. It can get up to 15 micrometers per pixel, so very, very detailed. And with that, we are able then to detect organic functional groups, such as carbon-hydrogen or, different carbon-oxygen bonds, different carbon-carbon bonds. We can then also look at some mineral species that are interesting biosignature, like carbonates, perchlorates, sulfates, phyllosilicates. So with that, we can then explicitly look for organic molecules, aromatic organic carbonic molecules, for example. So this instrument is very important also when we look for certain signs of life. These are the instruments that are both located at the robotic arm of the rover. And then there's some distributed throughout the body of the rover. We have MOXIE. This is very interesting. This is the, it's a demonstration instrument, basically. They want to create oxygen out of the carbon dioxide in the air.
Wow. That's for fuel, right?
Fuel and breathable oxygen.
Yeah. Of course, we need to breathe. I forget that.
Yeah. And it's actually a pretty important part, of course, of a human mission.
Yeah, indeed.
For the International Space Station, we have to fly oxygen up there. Or water and then make oxygen out of that. But yeah. So then we can produce it in situ. Then we have RIMFAX. This is a ground radar, which we can look into in depth of up to 10 meters. And with that, we can see the underground or subsurface structure, like a layering or some buried materials. It can also detect water and ice on a subsurface within 5 meters of the surface. However, the landing site was explicitly picked because it has no water within the first 5 meters of the surface. Basically because it's not allowed. So Mars has these special regions that they are called. And these are regions where liquid water may be present surface near, and we are not allowed to land rovers there because of contamination.
Yeah,
we want to protect the possible life.
Yeah, that's a pretty important part of all of these missions. That's what I came across all the time as well.
Yeah.
And of course, that's pretty important because, first of all, if you want to study something, you want to try and not contaminate it, because otherwise you've altered all future observations, and you'll have to take into account everything in terms of contamination that could have possibly taken place. And of course, if there was any life around, you don't want to disturb it.
Yeah. And these are like areas that we can look into in the future, when we can be more careful, when we have better techniques, maybe humans in presence on Mars, so we can be very careful and study them from maybe a distance or very, very carefully, so that we know we do not disturb them.
Yeah.
But to that point, they are a no-go area. Yeah, and then we have Ingenuity, the first helicopter on another planet.
Yay, finally.
Yeah, so that's a small, they call it helicopter, but it's like a drone.
Yeah.
It's very small. It has like two blades made of carbon fiber. It's a very light material. That two blades that counter rotate, because Mars has a very thin atmosphere, so it's a bit tricky to get it into flight. It has solar panels, and with that it gets enough energy for like 90-second flights per day. And it will do a series of test flights over 30 Martian days, starting in spring, within the next months, basically. It's currently located at the belly of the rover, and it will then be detached, within the next months, weeks maybe.
And it's more of a tech demonstration, basically trying to figure out how to fly in this atmosphere. I like there are these recordings of early tests, and Jesus Christ, this helicopter, it vibrates as hell. Like for real, it looks as if it could rip itself apart any minute.
Yeah.
These early
tests. It has to be like this high energy to get up into the atmosphere of Mars.
Yeah, that's what was really impressive. They showed these recordings during the stream, I think, as well. Yeah.
Yeah, drones are very useful on Earth, and they of course will be useful in the future, maybe for human explorations. But there are also some mission concepts that were actually approved already to Titan, the moon of Jupiter, that has a very thick atmosphere. And there's a mission called Dragonfly, which is a large drone, basically, that in the 2030s is going to study this moon. That's like the first flight of humanity on another planet. Yeah, and with that to the last part, and this is the sample return science, SRS, or sample return science. Perseverance has 43 sample tubes located at the belly of the rover. 5 of them will be used for blanks, so to see if the rover itself is contaminated. And there are 5 of them, so to get like in different time ranges to do a blank measurement to see if there's like a continuous contamination of the rover. And yeah, it can store then the samples at the belly, and then at some point it will just I don't know, it just sounds so weird. And then at some point it will place them on the surface, and these samples can then live within these tubes for like 10 years. Within this 10 years, they have to be then taken. And then they can also survive additional 10 years in orbit.
What exactly do you mean with they can stay there for 10 years until they're too degraded, or until...
Yeah.
bags
like
are
the
too
tubes.
damaged.
Yeah, I mean, probably a bit longer, but like the tubes have a lifetime. Like the ceiling has a lifetime for 10 years, they say.
Yeah.
And then, like, I think the danger is too high that they get contaminated by the Martian atmosphere or something like that. Yeah, and of course we want samples. But yes, the rover has very advanced instruments and it can be very precise. But having a human in a laboratory with really large instruments that some of them take up literally full rooms are of course more precise. And we of course can do more stuff here on Earth with the materials. And that's why we want to have samples.
Yeah, and you can be spontaneous about it here on Earth.
Yeah.
You can come up with new ways to study them, and maybe in a few decades someone will have a brilliant idea and you will still have them in storage.
Yeah. And the important part is, as I said, we now have Martian meteorites, but we don't know where they're from. We just know they're from Mars, but don't know where exactly they're from. And now we, because of the rover, we exactly know where the sample was taken. So we know the context in the region. And then we can do much more precise discussions and implications of the measured chemical abundances, for example. Since this is the last instrument, and before we will go into the landing site part, do you want to hear why I'm a bit afraid of the sample return part?
Yes, I was wondering about that when you mentioned it earlier.
Yeah, so my problem is, and I know that there are also some other people that are a bit afraid of that. That's like a main part of the whole project, you know? Sample return. That's one of the main parts. But all these other missions to Mars are still not yet even approved because they're just concepts. There is no lander currently existing. There's no transport vehicle that brings a sample back currently existing. There's no second rover existing that takes the samples. It's just concepts to that point. And you know how space exploration can be, really dependent on politics and stuff like that.
Yeah, of course. I mean, funding is a huge thing, especially for NASA.
Exactly. And I'm a bit afraid that these missions will get like pushed back and pushed back and pushed back to the point where they maybe, never happen.
I was thinking about the exact same thing when you said that they have to be recovered within the next 10 years, because talking in modern terms of space exploration, 10 years is basically tomorrow.
Yeah.
I mean, we mentioned before that it was pretty amazing that it only took this mission 8 years. 2012, you said.
Yeah.
Yeah, 2012. So 8 to 9 years.
Yeah.
To arrive there and to come to fruition. You were more into this kind of stuff, so I often don't have that much background knowledge because I don't know. I had the feeling, I thought that there already was something more concrete planned.
Yeah, and then also, the lander then will be made from NASA. But the small rover, which will then collect all the samples, will be made by ESA. And, ESA still has no... I mean, we have one European Mars rover, which is currently already built. It's waiting for its launch in 2022, so next year. But also we have, except for that, no real... knowledge about doing Mars rovers, so I found that a bit interesting. And also, I get the idea. We want to have samples from that have a large geological diversity, so all over the crater. And therefore, we cannot just have a lander that picks that up. We need a rover that drives around and picks them up. But still, I don't know, like a second rover that drives exactly behind Perseverance, not exactly behind him, but like all the way that Perseverance went, just to collect all the samples to bring them then back to a lander. I don't know, it just seems kind of unpractical. I mean, there are reasons for that, of course, but
Yeah.
I just wish that it was already finished, that they have all the things that they need, that it's just waiting there for the launch. It's just there and just waiting till they get enough samples to collect. And like that, it just seems like this, we will do that in the future, hopefully, Anyhow, that's about the rover and the instruments. And I guess you're going to talk a bit now about the geology of the region.
Exactly. Because talking about the mission is one thing, but why exactly did they choose Jezero Crater, and what's so special about this place? It wasn't an easy decision. That's what you get from researching that there were a lot of different contenders, but this is what they decided, this is where they decided to go, because this is a very, very complex crater with seemingly pretty complex history. So maybe to first give some very, very general information. The Jezero Crater is situated in Isidis Planitia, which is a region on Mars, north of the equator, to the east of the planet. Basically straight in the northeast of the Mars map. Isidis Planitia itself is about 1,200 kilometers across, and I read that it was presumably created by an impact. This is once again more your part. It's about 3.9 billion years old. And then Jezero Crater itself is situated in the northwest of Isidis Planitia.
At the highland boundary.
Exactly. It's at the edge towards higher elevations in the northwest. Basically, if you imagine having a crater, it's on the verge to the higher surface around it.
So the Martian is like this dichotomy. The Martian northern side is much lower in elevation and much smoother. And the southern part, the southern hemisphere of Mars, is much higher in elevation and much rougher. And that's why, for example, some scientists think that the north could have been filled in with an ocean before. And it's directly at that boundary.
Indeed. But also in general, it's you have this crater structure still, so the elevation around it is generally higher. Jezero Crater itself is about 28 miles across, corresponding to about 45 kilometers. And it was presumably also, created by an impact. So now we get into the more interesting stuff, and into the stuff which is of particular interest for the mission. This crater has rocks up to 3.6 billion years old. And now these deposits are very interesting because this is not just a simple crater. And if you have a bit of experience with geology, you can pretty quickly see that something strange is going on here, or was going on. I would encourage everyone listening to go to the website of the DLR, because they have a 3D map, an interactive 3D map of this crater, of Jezero Crater, and you can then go to different vantage points, and this could maybe add to what I'm about to explain right now, because you can then look around yourself freely. And it's pretty cool. It's actually pretty cool. And we're once again gonna link to that in the description on YouTube. So you have this crater. And what's pretty special now is that you have different channels. So you don't really have just this normal crater rim, but you have 3 very distinct channels crossing this boundary. This is one observation. Another pretty interesting observation is that you have very particular sedimentary structures present in the west of the crater, which on Earth correspond to river deltas. So think of areas close to the sea where water of rivers flows into the sea and where it just spreads out. You have these big triangular areas where the river basically floods a whole area. And you have these structures, so from these different channels, you have the western channel called Neretva Vallis. And this is where you have this big delta structure, delta type structure, which is approximately 5 kilometers west to east and 10 to 15 kilometers south to north. And what's interesting is you can actually see, structures which look as if they would have been produced by something flowing.
So
you have these straight structures from the west towards the east. And this is very distinctive there.
Yeah. I mean, it definitely looks like a delta. I know that some people are more careful about these things, and they call them often, also I called them in the work that I have done now, because I have a similar but much larger structure in the area that I'm working on. We call them more precautiously sedimentary fen deposits, because delta directly implies that there was water there. And of course, it probably was water, but you can be a bit more careful about it, and you call them sedimentary fen deposits. But yeah, it's beautiful, and you can even see, as you said, the different channels that were once there.
Yeah, and I mean, this is more meant in descriptive terms. So this is more meant as just giving you an image of what is present. And it's pretty impressive. It's really an impressive structure. You have the second inlet then more to the north, coming from the north, which is Sava Vallis, north to south oriented. It also has flowing structures, but it doesn't really look as distinct as the western delta. And what is also pretty interesting, and you can actually see that from these different vantage points in this interactive map from the DLR, the north rim seems to be less distinct and to slope way more gradually than the south rim. So think you have these channels in the north and northwest. You have this more gentle slope in the north. You have a less distinctive rim of the crater. And what this would suggest in general is that potentially erosion took place there. And that sediment was deposited, and which created in turn slowly this gentle slope. And this is what I found pretty impressive, because you can actually recognize that in the 3D map. But this is basically what you can observe with your own eyes. There is a lot more going on, because Thomas already talked a lot about spectroscopy. So basically looking at the spectrum of light emitted from the surface, and what spectroscopy data for this particular crater has suggested in the past was that there is, well, carbonate present. And once again, Thomas discussed this earlier, this is on Earth pretty often connected with water. This is oftentimes connected with life, because a lot of plankton here on Earth, and in general a lot of microscopic life forms, tend to form calcitic shells or calcareous shells. You have clay minerals present in some way, shape or form, which incorporate water into their crystal structure. So this is all something we know from Earth being connected to water. And it's not even only that, because I read a paper which went more into detail with that, and they, for example, stated that there are a couple of different carbonate deposits, that it seems that they could be connected to one another, but it's pretty complex, because some deposits seem to have been some deposits seem to contain redeposited material of former flow systems. It's all pretty. We know that some redeposition has taken place there. That's the point, I think. And something pretty interesting I read was that there's smectite present, iron magnesium smectite. And that's pretty interesting, because that's what we know from Earth once again. This is created when basalts weather on Earth. You know what I mean?
Yeah.
So, once again, good indicator that redeposition has taken place. There is a lot going on. A lot of hints at water flows into a large lake in this crater. There could very well be signs of life. These calcareous deposits would be very good contenders as basically deposits hinting at former activity of life, if present. And all of this makes this very particularly interesting.
Yeah. There's a lot of evidence that water was there at some point. So when we talk about water on Mars, this fluid water in these surface, water bodies existing on the surface of Mars, then we talk about time scales around 3.5 to 4 billion years ago. So that was extremely long ago. But
exactly. It's I've read it being suggested that in general, about 3.8 billion years ago, activity would have ceased there.
Yeah.
3.9, 3.8 exactly. I mean, all of this seems to have taken place in the late Noachian period. So it's supposed to have been a pretty wet time. But I mean, that's the interesting thing. You have these indicators at redepositional processes, which we only know in connection with water here on Earth. Truly, you have hints at water. As the old saying goes, follow the water. If life was there, this might have been a suitable habitat. And this is the reason why they want to look into these deposits, why these are good contenders for potential. I mean, not even only for life, but in general, this could really give us an idea of how deposition on Mars worked, and the mineral assemblages are of key note here, because once again, these minerals, they contain water. We know that here on Earth, they are connected to flowing water, and to weathering processes, and this alone is very interesting. If we don't detect any signs of former life, it's a pity, of course. It would be spectacular if it happened, but even if not, it's very interesting to find out more about, well, how hydrodynamics on Mars worked, how hydrogeology worked. And I mean, you told me once before that there have even been suggestions that maybe there can be other explanations than a large ocean or large lakes for all these structures.
Yeah, that's what, for example, I'm currently trying to figure out for my region, the presence of water and in which type the water was there, and it's extremely complicated. Stratigraphy on Mars is so complicated because we can just look at it from space, and there is so many question marks that we still have. That's a very active discussion, and to be honest, in many parts we have absolutely no clue. And yeah, that rover can do a lot for that.
Yeah. So
also, maybe to add, if we don't find there any evidence for life, this of course does not mean that there was no life on Mars. It's extremely difficult to find signs of life that are over 3 billion years old. That's an incredible long period of time, and also that's just a so small spot, on Mars.
Yeah.
And the rover can just do, in the end, in a small area. So maybe just some 100 kilometers farther north, I don't know. Maybe there is the evidence that we searched for all the time, but we've never saw it with the rover. Yeah.
You never know. It's a shot into the blue, but yeah, it's a very fascinating region regardless, and that's the important point, I think. It's a very interesting region. I mean, just seeing these structures alone, I realize right now that I forgot to say this, but there's also an outflow, which is pretty important because you have these two inflows I mentioned, Neretva Vallis and Sava Vallis, but there's also an outlet flow, for example. So you can even see this one. It's directed, or it's positioned in the east of the crater. And you can see that there was some kind of an hydrodynamic system. Something was going on there. No matter what happened there are a lot of question marks, but yeah, that's why our little friend Perseverance is up there or over there. Yeah. And we're going to be listening eagerly to what he has to say, or it has to say.
Yeah, we can say he.
Is it a he?
Yeah. Perry is like his, or Percy is his nickname. And also, since it's such an interesting topic, and as I said before, I'm working on a project that it's connected to the ESA Mars rover that will launch next year, which is also built for the search for life. I think we can actually do an episode about that topic once, because there are many things that I have worked on, for example, will work on, for example, the sedimentary history. In my region, for example, is the largest sedimentary fen on whole Mars, probably. Then we also have phyllosilicates, so the clay minerals that you talked about, and they're very interesting, and you can actually say a lot about them. So maybe I think we will come back to Mars at some point.
Absolutely. It's just a too interesting place to stay away from. I mean, there are a lot of interesting places in our solar system alone, and you know what keeps amazing me is that no two places really are the same. It's still, I find it a bit strange, actually, in some ways, that everything seems to be pretty different. But yeah, Mars, it's just Venus and Mars, they both seem like Earth 2.0 potentially gone wrong, and this is so fascinating. One has an atmosphere which is turned into the absolute hothouse and is now one of the most hostile things you can imagine, and the other one let go of its atmosphere. And just these two very, very contrary extremes I find very, very interesting.
Oh yeah, definitely. I don't have the time in view because my counter for some reason restarted.
Oh, we're running long, don't worry.
Okay, then maybe let's end on one question that I want to ask you, and then I will answer it myself. And let's try to answer in just a few sentences.
Oh dear.
A 2-part question. Or no, maybe 1-part question. So and of course, there's no scientific meaning behind it. It's just something I wanted to ask. Do you think that there could have been life on Mars once, or there would have been life on Mars once, and very surprised if we would find signs of life, or if we find no signs of life, basically?
I wouldn't be surprised in the least. Like, for real, of course, I would be overwhelmed, because this would mean we're not alone. And this would be the announcement the past century of astronomy worked towards, and just think about the philosophical meaning this would have.
Yeah,
the emotions you would feel.
At that point, humans will no longer be something. I mean, we still be something special, or life on Earth, not humans. Life on Earth would be not something special anymore, still, but it will be statistics. Yeah. It will be just one other dot in the plot.
Exactly. We would finally have a sample size of 2. And this alone, this is an amazing and an incredible thought. But with the first few days, weeks, months having passed, I think looking back at that particular moment, it would not have been a surprise for me. Absolutely not. Given the conditions which could have been present there, and given what we know life to be capable of, on Earth alone, let alone the fact that who knows what else, what kinds of forms and shapes and capabilities life could have somewhere else. I mean, just think about what's going on with the whole Venus discussion right now. Yeah. Enough sentences. What do you think?
Yeah, I will put it actually nearly the same way as you did. I would not be surprised if we would find evidence of life. I would, of course, also be overwhelmed, but I would not be surprised. But also, at the same time, I would not be surprised if we would never find any evidence. It's like either scenarios. It's so likely there could be life, but that still could have been life, but it still does not say that there had to be life. There's so many unknowns that we still have, and maybe there was life and we never find the evidence for it. There are so many question marks, but either way, I would not be surprised, but of course overwhelmed if we will ever find the evidence.
Maybe I think I didn't answer this part of the question, but do you think there was life? Do you really think that?
I mean, that's so difficult to answer, but I mean,
just your feeling, your gut feeling.
Yeah. There definitely was I think there was an habitability of some regions on Mars that could definitely have formed life. And I personally, since on Earth life formed basically so fast, I personally think that might have been possible, yes. I think that maybe even on a very small regional scale, but I think that it would have been possible, yeah. This of course has absolutely no meaning to it because just
Yeah. But that's what I was asking. Just your gut feeling.
Yeah, I say yes. I think I tend to say yes. Yeah. I mean, normally I would say could be either way, but if you directly ask me, I would say yes.
This is not based on reason. I am more of a pessimistic guy, and then I am often the one who tends to go for the less spectacular explanations, and so my gut feeling would actually be no.
Yeah, because I personally think that life is nothing spectacular. You know what I mean? I think that life in simple form is maybe even for spread. But to be really fair, early Mars was a hellhole. It was not this beautiful. Oh, there's an ocean and we have beaches. That's 3.8 billion years ago. To that point, still very large impacts happens on like a regular basis and stuff like that. So it was definitely no easy place to live.
But early Earth wasn't either.
Yeah, that's true.
It's just I don't know. Really, if I would just have to, and of course I'm not really in that kind of field of research, but just my pure gut feeling, I don't know. It says there wasn't life. It's absolutely reasonable to assume that it was just compared to Earth, I think, but it's just a pure feeling.
I mean, it's an incredible topic, and I actually find it very interesting or very cool that we have maybe different gut feelings about this. And just about the history of, or like the habitability of Mars in general is also a very interesting topic that we also probably will get back to.
Yeah, like all these different topics, we oh Jesus,
yeah,
this list, we have so much to talk about, and yeah, that's always the most fun part, this little discussion at the end, I think.
Yeah, I really enjoyed it, especially at that point because there's so much more that I have in my mind because I kind of worked on that, you know, but I have to take myself back.
Yeah, and that's the cool thing. You're actually involved with stuff like that. And yeah, just imagine what could come from this mission right now. What we could know in a few months' time. Who the hell knows? Maybe we'll have an incredible answer just around the corner. And although, yeah, it might not happen, it could. It very well could.
Oh, yes.
But of course, then again, you'll have to go through a lot of different fail-safes and retesting and reevaluating as science does, but... Okay.
That was synchron. I think that concludes the episode for today. I hope you got some kind of overview of the mission itself. To like know what you maybe can expect in the future, and we will probably give updates to that mission all the time once there is something new happening. So yeah.
Yeah, especially if something incredible happens, but let's see.
Yeah. So thanks for listening and goodbye.
Bye, guys.
Thanks for listening to the RockyTerrain podcast. If you enjoyed listening to us, please consider subscribing on your favorite podcast platform. Everything addressed in this podcast reflects our own opinion. You can contact us at 4.5gainthemaking@gmail.com. That is 4.5gainthemaking@gmail.com. All music used is from Kevin MacLeod and was downloaded from filmmusic.io under the Creative Commons license. That is heavy interlude for intro and outro, and home bass groove for intermission.
How about it's
What do you want to tell us?
Speicherplatz.
Oh,
German word of the day. The second or third this time.
Interestingly, I never used a German word. I only used English word, but now I can figure it out. Yeah.
No, it doesn't come to mind.
I will cut here, so that's a bit faster.
Yeah.
But what? Storage space, right?
Yeah.
Storage.